So what is TensorFlow? Let's start with that. Okay, so goal of this talk is introduction to main TensorFlow concept. It will be useful to have a mental model of how system behave, TensorFlow behaves. Mostly you can forget everything and use high-level wrapper if your job is just to use machine learning, right? Machine learning algorithms out of the shelf. If you're a researcher or developer of machine learning algorithms, you should also know low-level TensorFlow. Okay, so what is TensorFlow? So TensorFlow is open source machine learning library. I'm sure all of you know about it. It's originally developed at Google, and it has been open source since November 2015. It is one of the highest rated repository on GitHub right now with 65,000 plus stars. TensorFlow is especially useful for deep learning, but how many of you are non-computer science people? Okay, quite a large number. If you want to run some of the mathematical simulations, right, or any complex mathematical calculations, you can also use TensorFlow for that. That's something that I want to emphasize on. Otherwise, people generally feel that TensorFlow people generally associate it with only machine learning, right? There are machine learning libraries built on top of TensorFlow, but core TensorFlow is not really tied to machine learning. So you can define any mathematical computation as a data flow graph, as we will see in a few minutes, and then you can run it on a TensorFlow. Right? You can use TensorFlow for research as well as in production environment. So if you are doing startup and thinking of using machine learning, you can think of TensorFlow, right? You can use TensorFlow. TensorFlow is equally also useful in research, where I have seen trends where a lot of researchers are actually writing TensorFlow code and making it available to the community so that people can experiment with that code later, right? And TensorFlow is open source with Apache 2.0 license. Right, so there is some meaning in the name TensorFlow, right? Did you ever wonder why this name TensorFlow, right? It's actually a combination of two words, tensor and flow, right? What is really tensor, right? Have you taken advanced mathematics course? Right, so tensor in this context is multidimensional array, right? Tensor is nothing but multidimensional array, and flow is nothing but a graph of operations, right? Every mathematical computation is expressed as a graph of operations in TensorFlow. So the nodes in the graph are operations, and the edges are nothing but tensors. So tensors flow into operations, right? So imagine doing a matrix multiplication operation, right? Or a vector matrix multiplication. So vector and matrix will be the input, and matmul is the operation. Okay, so Google is using internally TensorFlow very heavily. Do you recognize all these logos? So Google uses TensorFlow heavily in all these products, right? So you can see that the number of directories containing model description file has just gone up very heavily, right? So we start with high-level design of TensorFlow, what exactly it is. Right? So TensorFlow defines a general purpose computation graph. Right? It achieves ease of expression, and then it creates tools for running it in different environments. Right? So one really good part about TensorFlow is this, right? TensorFlow can execute operations on various hardware platforms. Right? So you have CPU, you have GPU, you have Android, iOS, or Raspberry Pi. So even if you are writing some kind of an embedded system, you can still think of using TensorFlow and put it on embedded system. How does TensorFlow achieve that? So there is something called as TensorFlow distributed execution engine, right? So we generally write our code either in Python, C++, Java, Go kind of front end, right? So TensorFlow distributed execution engine takes your code written in Python. So this TensorFlow distributed execution engine takes the code written in Python and converts it into the underlying hardware instruction set, okay? So it's very useful to understand this layered API of TensorFlow. It will help you to know exactly what is useful in your work. Okay? So this is what I was talking about. So this is core TensorFlow, right? So you can write your mathematical operation as a data flow graph in this Python front end. Then TensorFlow distributed execution engine takes it and using this, you can run it either on CPU, GPU, Android, iOS, Raspberry Pi, right? So one really good thing about TensorFlow against the competing libraries is that if you write program in some other competing library, like let's say scikit-learn. Do you write scikit-learn? Right? What do you do to distribute a program? What do you do to write a scikit-learn on a very large amount of data? Right. So essentially, when you have large data that is distributed across system, right? Obviously, there is nothing in the scikit-learn API. Right. So you will have to essentially do all the work of distributing the computation to 10 different nodes, right? And then collect the result of that and do training in a distributed fashion, right? Using TensorFlow, you don't have to do any of these, right? You can simply specify your data flow graph and let TensorFlow handle the complexity of the distributed system. So TensorFlow, once you specify your cluster, once you give cluster specification to TensorFlow, TensorFlow decide which operations to schedule on what kind of device. Got it? So that's one of the awesome thing about TensorFlow. Okay, so I'll repeat the question for benefit of everyone. So your question is whether there are different APIs written for this different hardware platform. You don't have to worry about it. That is handled, it's handled internally by TensorFlow. So I think it might have written some kind of layer, right? Some kind of layer will be there that takes the high level code, and then there will be a layer to write instructions that can be executed in CPU. So if you are written program in Java, for example, right? So you can think of this as a compiler or a Java virtual machine, right? So virtual machine takes the Java code and then it can execute it on different operating systems, right? Windows, Linux. You don't write different Java programs. So for GPU, there is no Java analogy, right? So what happens is that your data flow graph, right, that is written here. So you specify your operation in form of a data flow graph. TensorFlow takes this data flow graph and it generates some kind of an instruction in order to run it on CPU, GPU, Android, iOS. And internally, TensorFlow will have all the information, right? So that's part of the TensorFlow internal, right? We are not worried about that as a developer. So TensorFlow will have a way of converting your instruction so that they run on CPU, GPU, and all these kind of things, right? So let's say if I ask you to, I give you two jobs, right? Add two numbers, add a comma b. Will you be able to write that function? Add a comma b. Pretty easy, right? Now I ask you slightly harder question. I give you a photograph and I ask you detect face of a person in the photograph, right? Can you write a program for that? Yeah, so maybe you can construct features by hand and then write rules or something like that, right? But rule-based systems are brittle, right? If I take a photograph of a person from slightly different angle, right? Probably it will not work, right? If you write rules that are hand-coded for a straight face, right? Straight camera-facing face, right? So what's the difference? Okay, I want you to take a step back and think about the difference between these two tasks, right? The first task is write a program to add two numbers, and the second task is find a human face in the photograph. What's the difference between these two tasks? So essentially in the first task, you know the function, right? You know the exact mapping, how to take two numbers and perform addition, right? You know the function, f of a comma b is a plus b, right? But in the other task, unfortunately, we do not know the function. So f of a photograph, right? And I want, let's say, output of 1 if face is present, 0 otherwise, right? I do not know the function, correct? But as a human, you can easily recognize it, right? So why are we able to recognize that? Right? Our brains are trained to recognize those kind of images. Right? Now, can we do similar thing with computers? Right? Yes, you can. Right? So that's what is machine learning all about. Right? So what do we need to do machine learning? What's the first and foremost important thing? Data, right? Training data. And you need a lot of training data, right? So you need to have training data. In this case, you need to have a label training data. So you need to have photograph and a label associated with it, which will tell whether there is a face or not. What do we do with training data then? Right, we need training data, that's the first thing. What else? What else is required in order to build machine learning model? training data, test data is covered, right? You need model itself, right? Model is the first thing. What else? Cost function, right? You need to have a way of evaluating whether machine learning algorithm is performing correctly, right? So cost function is another thing. What is the third thing? Once you have cost function, you need to have optimization algorithm, right, to optimize that cost function. And fourth, you need some kind of an evaluation criteria, right? So one very, very simplified or componentized view of machine learning is putting machine learning algorithm as a point in this four-dimensional space, right? You have model, you have cost function, you have optimization objective, and you have evaluation criteria, right? So think about any machine learning algorithm, and you will be able to put it as a point in four-dimensional space, right? So what are some of the examples of models? Tell me. I mean, it's important in this context. I'm actually building up the context so that you understand what is there in the layers API, right? So what are the example models in machine learning? Decision tree is one model. Neural networks, linear regression, right? Theta transpose X, right? Logistic regression, right? Which is the, we take linear combination and put it through logistic function, right? So these are all models, right? Then what are the examples of cost function? What do we use as a cost function in regression kind of problems? Least square errors, very good. What about classification? Cross entropy, right? So these are cost functions. What kind of optimization algorithms do we use? Adam optimizer, the most gradient descent, right? Stochastic gradient descent. These are all, there are many of them, right? So these are all optimization algorithms. And what are the evaluation metrics? So accuracy is one. F measure. Is accuracy good every time? Where does it fail? Whenever you have imbalanced kind of problems, right? Accuracy is a bad measure. Let's say you are asked to write a program to detect spam emails, right? And let's say spam emails are just 1%, right? I'll write a classifier which says that everything is good. Accuracy is 99%, right? Are you getting what I'm saying? So accuracy is a bad measure in such case, right? So we care about what is called as precision, recall. Do you know all these things? Precision, recall. Have you heard about it? Have you heard about confusion matrix? Yes. So all these are bare nut and bolts of machine learning, right? These are all reusable components in machine learning, right? You take any machine learning algorithm and it will have these components, right? So I'll give you one secret mantra of knowing machine learning. When somebody comes to you and says that I have invented a new machine learning algorithm, right? Don't get worried, ask 5 questions, 4 questions, 5 questions. What is the training data, right? What is the model? What is the cost function? What is the optimization objective? And how do we evaluate this algorithm, right? If you ask these 5 questions, everything will be sorted out. Got it? Okay, so these are all reusable machine learning components that are defined in layers API. It's very important to know what is where in TensorFlow because it's very easy to get lost, right? So we talked about so far about Python frontend. This is all about writing your mathematical operation as a data flow graph in layers. So these are now machine learning specific APIs, right? So in layers we have all the reusable machine learning components. Then people said, there are why should I care about building models using layer all the time, right? Okay, so people said that I don't want to always use this layers API, right? I need some higher level abstraction to define a new machine learning model, right? So if you are doing your MS project, research, or even BTP, where you need to write your own machine learning algorithm, right? New algorithm, you can also think of using estimator APIs, right? So estimators you can think of estimators as abstract classes, right? Do you know abstract class? Huh? So it defines some kind of a framework, right? So for any machine learning algorithm, if you want to use estimator, right, it says that you have to implement what is called as train function, model function, and test function, right? So estimator is a framework to build any machine learning model, okay, new machine learning algorithm. And then people said that why should I keep writing the same linear regression? Why should every developer should write same linear regression using estimator, right? So that's why TensorFlow came up with canned estimators. Right? So in canned estimator, TensorFlow is supporting linear regression, logistic regression, and neural network out of the box. Right? So if you want to use TensorFlow just like scikit-learn, just like scikit API, canned estimator is your answer. Got it? So that's what core TensorFlow supports. Outside TensorFlow, so there are some other third-party canned estimator for decision tree, then SVM, and for clustering. Random forest is also there. There are 3 canned estimators supported, 4 rather, supported in the core TensorFlow. One is linear regression, logistic regression, deep neural network for classification and for regression. Right? These 4 are supported by TensorFlow implementation by Google. In addition to that, there are third-party implementations for random forest, SVM, and for clustering. Okay, so this is essentially a data flow graph, right? This is a data flow graph for calculating, for performing ReLU, right? A basic operation in neural network, right? What is a basic operation in neural network? We have examples here, right? There are weights on each of the feature, right? So we do theta transpose x, right? And right, so we do matrix multiplication of examples and weights. This is a vectorized implementation of neural network, for example, right? So we take examples and we take weight, we do matrix multiplication, right? So this is a mathematical operation. I want you to look at the nodes in the graph. Each node is a mathematical operation, right? And edges are the one on which we send the tensors or multidimensional arrays, right? So weights are coming on this edge, examples are coming on this edge, and there is a matrix multiplication happening here. And the result of the matrix multiplication is fed into the addition operation, right? And that is added with biases, okay? And result of this entire add operation is fed to ReLU, right? Rectified linear units. And then we do another extent operation between labels and whatever you get out of ReLU, right? So why does TensorFlow define data flow graph? So in a classic TensorFlow, now we have what is called as TensorFlow eager, in which you can define operations and run it as you go, right? But in a classic TensorFlow, as when we started, there were 2 distinct steps, right? The first step is about defining a data flow graph, and second step is execution of the data flow graph, right? Why do you think TensorFlow has this design philosophy? Why are these 2 separate things in TensorFlow? Let's try to understand that. That will help you understand why TensorFlow first insists on laying out a data flow graph and then executing it. So what are the advantages that TensorFlow will get by doing this? Now you can see that I can perform this matrix multiplication operation in, let's say, GPU, right? Let's say GPUs are good at matrix multiplication. I can take this piece of graph and schedule it on GPU, right? Then I can perform this addition on CPU, right? So it knows exactly the dependency between the operations, and it can decide which operations can be parallelized, right? And when TensorFlow, we'll see it in a moment. Yeah, so these are, we talked about it, edges are n-dimensional arrays that are tensors, and computation is a data flow graph. Yeah, this is what happens. Now TensorFlow can distribute the computation, let's say, to device B and device A, right? And now you will wonder, now there are 2 devices, right? What is required? Some way of communicating, right? You need a notion of communication. So that is handled by TensorFlow. So TensorFlow will include send receive nodes automatically. You don't have to do that. Are you getting what I'm saying? So imagine you yourself implementing such a distributed training. You'll have to do all these things that TensorFlow is doing for you. That may be partially answering what your questions are. Okay, got it? Any questions on this? Yeah, so this, look at it. Send receive nodes are put there. Then it also puts some other mathematical operators, something like differentiation, right? Automatic differentiation, right? Where do we use differentiation in machine learning? Huh? In optimization, right? Whenever you are trying to optimize the parameters, right? We use, in gradient descent, we take partial derivative of what? Of loss function or cost function, right? So if TensorFlow doesn't do it, you would have to supply a function to perform the differentiation operation, right? But TensorFlow has inbuilt facility to do the differentiation, right? And it actually inserts this node automatically, right? Plus TensorFlow also has a specialized linear algebra operation compiler that also optimizes some of the mathematical functions for you. The way you can think of this as a compilation phase, and all kinds of optimizations are done at that stage. Right, these are basic send receive implementation. Right, now this is where the extensibility comes in. You can, there are a number of standard operations and kernels. You can also define your own operators and kernels in TensorFlow. Okay, if you want to extend TensorFlow to support new kind of hardware, TensorFlow gives facility to write your own operations and kernels. These are device-specific implementations of operations and kernels. This is where you can explore if you want to support new kind of hardware, right? Right. So this is a single process configuration. So there is a client. So what happens is that first we define a data flow graph, and then we run it in a specific context, right? So we create a session, and every data flow graph is executed in that context, in the context of that session, right? So if it's a single process configuration, we say that session run, which then executes the subgraph on the worker, right? In a distributed configuration, what happens is that the master process spawns multiple workers, right, and get the work done. Okay, and what you see here is a graph of this is a TensorFlow graph for neural network, right? So you have a logit layer, you have a ReLU layer, you have input, you have reshape operation here, and this is stochastic gradient descent trainer. Okay, you can see that this is a tensor. This is basically neural network graph. Okay, in practice it can be very complex with hundreds to thousands of nodes and edges, right? But you are insulated. If you are writing at layers API, you don't have to deal with writing a data flow graph of the low layer operation, right? Because layers will have already implemented some of these subgraphs. For example, this HGD trainer might be already implemented by the layers API, right? In the same manner, there is logit layer that is already implemented, or ReLU layer that is already implemented for you, right? So we will see. I mean, in course of the workshop, we will look at building TensorFlow model right from candidate estimator to the low level API. Okay. All right, let's peep into the second one, Python front end. Right, so we already talked about data flow graph, right? So that's the core of TensorFlow, right? So this is how you build your data flow graph. So import TensorFlow as TF is the standard import. Then this is how you define your session, right? tf.session. Okay, so we define session, right? And then we are now defining a data flow graph, right? So tf.constant, right? So this is a way of specifying a constant tensor called constant multidimensional array. And I have a two-dimensional array. The first row is 5, 6, second row is 7, 8, right? And then I'm performing the multiplication of this X tensor with itself, right? Now this is only defining, it is only defining a tensor, right? It does not right now have any value in it, right? So we will see actually in a lab when we say print X, it will not actually print the content of this tensor, right? It will just print that X is a tensor of type constant, okay, and it holds probably numeric values. So that's the information you'll get, right? In the same manner, Z is another tensor, right, which performs first multiplication, then it adds another multiplication to it, right. So this is multiplication between the matrix X to itself, right, and then we are doing multiplication of X with an indicator matrix, right, or a diagonal matrix which has 1 on the diagonal. Getting it? Right, and then there is addition operation. So you can now you can see how this graph is actually represented here, right. So you can see that there is a constant X, and there is another constant which is this constant matrix, right. These are my input tensors, right. So this constant is multiplied to itself through matmul operation, right, and then there is another matrix multiplication happening between this constant matrix and the diagonal matrix. Got it? That is represented in this matmul operation, and then I am performing addition of these two. Result of this matrix multiplication operation is added to the result of this matrix multiplication operation. And when I do z dot eval, right, that is the time when we are executing this data flow graph, right, and we are saying that I should evaluate z, which is this particular node, this particular thing, right. I can, in the same manner, I can say that evaluate x, then it will evaluate this, only this part of the graph. So you can evaluate at any part of the graph, right. You can lay down your complete graph and then evaluate any subgraph of that particular graph. That is okay. Got it? But you have to run it under tf.session. So let's do this first basics of TensorFlow practical. Okay, this is something that I'll run on my screen. So do you use Python? You people are familiar with Python? How do you write your Python? You write your program and then execute it. That's how you work, right? So Jupyter Notebook is a very nice way of building demos, right? Where you interleave the documentation and the code. Right? Otherwise, what do? Are you research scholars or are you running your company? What is it? Research scholars? You must be writing demos, right? Let's say you want to quickly try some method. Right? You read a paper and you want to try it and show it to your advisor, right? What do? You will write the program in some separate file, and then you will write you will have paper that will be separately in a separate document, and then you have to constantly refer to the paper and document to explain that. The Jupyter Notebook solves that problem for you. So Jupyter Notebook gives you a way where you can write some document, right? And then you can write a code block, right? So what you can do is when you are when you are implementing some research paper, right? You can start with a Jupyter Notebook. You can run this locally as well, right? And you can write documentation like this, right? So I have written some documentation about basics of TensorFlow, right? And then I can run now. Okay, so basic unit in Jupyter Notebook is a cell. There are two types of cell. So this is a text cell. And then second cell is the code cell, right? I can run this code cell by pressing this run button, right? So now this code cell has run. Let's say if I want to do something, print finished import. Okay, you can see this, right? So you can run this Jupyter Notebook cell by cell and see the output, right? So let's say you want to demonstrate two competing approaches, right? So you write your code for first approach and second approach. In the same document itself, you will be able to get all the comparisons done. Is the idea clear about Jupyter Notebook? For those who are not familiar with it, right? You can run it cell by cell. Okay. Let's print hello TensorFlow, right? This is a tradition to print hello world in any language that we learn, right? So let's see how to do that in TensorFlow. All right, I have some output that I'll clear first, right? Current output clear. Okay. So what is it that I'm doing here, right? So I'm defining a hello tensor, which is holding a constant, right? Which is holding a TensorFlow constant tensor with value hello TensorFlow, exclamation mark. Okay. Now let's print this hello and see what is there in that. We have already talked about it, so I have already leaked the question, no point asking this question again, right? And then I define this session, tf.session, and I say session.run, hello. Okay, let's see what comes out of this. Okay, so the first print has printed, see this, what it has printed. This is a description of a tensor, right? It says that hello is a tensor, constant colon 0, right? This is a automatically generated name by TensorFlow program, right? Second most important thing is shape of a tensor. Since we are talking about a scalar, the shape is, do you use NumPy? How many of you use NumPy? It's the same concept as NumPy, right? And the type is string, right? Type of this, the type of object that this tensor will hold will be of type string, okay? And the second print, second session.run print actually prints hello TensorFlow. Got it? This is the point that I was trying to emphasize earlier, that if you just do print hello, right, without running your node in the context of session, you don't see hello TensorFlow, but you see the type of or the description of the tensor. And when I run hello in the context of a session, I see hello TensorFlow. Got it? Okay, so this is how you can define constant, right? You can define a scalar. You can use shape and rank. Let's print them, right, and see what comes out as a shape and rank. So shape is 0 in this case. So for scalar, shape is 0. Now let's look at what is the shape for a list. So you can see tf.constant. I can define a list also, right? So this is a rank 1 tensor, right? So let's print the shape again. Okay, except this workshop, except this basic thing, I give all the notebooks to you to execute, okay? So you will not be bored. So you can hack, you can keep writing in this notebook and see what comes out of this. So here the shape is null, right, because it's a scalar, right? When I have a list, right, you can see that the shape is 3 here because I have 3 elements in the list. Now let's look at, I can also define 2D, so I can also define a matrix. Right, this is a matrix which has 2 rows and 3 columns. Let's look at the shape of that. You can see that the shape is 2, 3. There are 2 rows and 3 columns. You can also define rank 3 tensor here. So I can see print extensor here, right? You can see that the shape is 2, 1, 3. Right? I am defining a 3D array here. Okay, got it? Any questions? Okay, we'll shift the gears now. Now this is how you define A plus B. So I am defining 2 arrays, right? 2 lists, and I can do I can add these 2 lists just using a simple addition operation. Right? Let's try to do this. So this is defining data flow graph. That's why you see the information of the tensors. And now I'll define a session and run total, and you will see that 3 plus 4 is 7 that you see here, and 2 plus 1 is 3 that you see here. Got it? Okay, so that was about constant. Constants are not interesting. We talked about it. Right, so what is the most important thing in machine learning? We talked about training data, right? And you cannot have your training data in memory, right? I cannot really write training data as in-memory objects and hope to input them to tensor, right? So your training data will normally be in a database, or you might have a file, right? Big file, correct? And now you need to know, you need to have a way of inputting this file in TensorFlow, correct? So tf.placeholder is your friend for that. So you should use tf.placeholder. So this is more like a promise. I am promising TensorFlow that I will input, you know, an object or bunch of values of float 32, right? And hold a place for these float values for me in tensor x. Then in the same manner I will define another placeholder for y. So in x, in this case I am going to hold all my inputs, in y I will hold my labels, for example, and then I can do z equal to x plus y. Right now, since I am doing placeholder, there is a specific way in which you have to feed data into this placeholder, right. So we need, we use a mechanism through feed dictionary. It is more like a dictionary, right, where I can initialize values for the placeholder. Are you getting what I am saying? Huh? In the back? Okay. So here I have initialized my x with value 3 and y with value 4.5. Instead of saying that x and y are constant, I am saying that now there are placeholders and I am inputting them through feed dictionary, right. And I will run this z under session object, right. I will run this. In the second instance, I am actually initializing x and y to lists, right. One has 1, 3 and second is 2, 4. And when I run it, I see the first print statement has printed the sum of 3 and 4.5, that is 7.5, correct. And second print has printed the sum of two vectors, right, which is 3, 7, 3 and 7. Yeah, no rocket science. I mean, I am just demonstrating how you can use TensorFlow to perform this basic operation. Yeah, feed dictionary is a mechanism of putting values into the placeholder. So tomorrow, I mean, let's say we will see this in the workshop. When I am reading data from files, I will read it in memory first from the file, and then I will use feed dictionary mechanism to initialize the placeholders. I think TensorFlow Eager helps you to do operations as you lay your data flow graph. We are not going to cover TensorFlow Eager today. In a classic TensorFlow, the way it started, this was true till API 1.6, right, where you have to first define a data flow graph like this, and then it's important to run it in a tensor in a session. So let's say if you have two graphs, I will put it in another way. You can define two data flow graphs, right, and then you can define a session for a graph and then run the session within that graph. So you have to associate a graph to a session and then run it. Right? If you don't specify any graph, then default graph is run under the session. You will have to start a session and specify what graph you want to use for that particular session. We can also define variables. Right? So for example, in machine learning algorithm, we also need variables, right? Variables like variable to hold weights, biases. These are classical variables in programming language, right? Variables that can take different values in the course of program. Okay, so let's go back. Okay, so that was the first practical which I walked you through, right? This point on what are practicals now on that will come, you will be doing it on your own. Okay, so I'm going to start slightly in a reverse manner, right? So we looked at here, right? Now we will go all the way to the top, right? This is for people who do not know much about TensorFlow and people who just want to use TensorFlow like scikit-learn API, right? So for the benefit of those people, we will start from here, and then we will go into deeper. Then we will go to Layers API, where you will actually be writing your own machine learning models using Layers API. Okay, so the first practical will be pretty straightforward and easy for many of you. So let's look at canned estimator. How many of you have written scikit-learn API? How many have you written your machine learning in scikit-learn? Oh, so not many of you have written machine learning programs? How many of you have written machine learning programs in some language or the other? Okay, so what language do you use? Python, but in Python what do you do? PyTorch, okay, fine, PyTorch, okay. So if you are using PyTorch, you should also try TensorFlow Eager. It's very, very similar. Okay, fine. So let's look at canned estimator. So this is a code snippet for canned estimator. You can, if you have written scikit-learn program, you will see that this is very similar to scikit-learn, right? So I use, so in TensorFlow there is another concept called feature columns. So feature column is a concept to give input to the TensorFlow canned estimator, right? So you have to use what is called as, so you have to specify what is your data type. So I define one real valued column, square foot, then rooms, which is another real valued column, and then there is a zip code. I'm saying that is a sparse column with integrated, with integerized feature, right? So TensorFlow gives you, so there can be multiple types of feature in machine learning, right? So how do you handle discrete values in machine learning algorithm? Let's say you have a feature called color, and color red, blue, green. How will you represent this red, blue, green so that computer understands it, right? So one possible way to represent red, blue, green is using, let's say, three variables, three binary variables, right? So when red is on, I will put the first variable as 1. When the blue is on, I will put second variable as 1, and when green is there, I will put third variable as 1. It's called one hot encoding. That means out of these three variables, only one will be on at a given point in time. So this is a standard way of handling your categorical data. But this is not the only way. So sometimes what happens is that if you are doing natural language processing and then there are words, right? So you will have this one hot encoding running into millions of dimensions, right? And you want, let's say, some kind of low dimensional representation of this thing. So there is something called as embeddings, which is more like a continuous representation of the words in much lower dimension, right? Because what happens with one hot encoding is that you get large amount of sparse features. There is a lot of sparsity that gets introduced in the training data, and embeddings is one way of reducing that sparsity and getting dense representation. And then I just use this linear regressor function and feed the feature column into it, and that's it. I have a regressor, okay? And then I say that, regressor.fit and regressor.evaluate, right? So fit will do the training and evaluate will do the evaluation.
Are there any other things other than that sparse column with integrals permitted?
Yeah, there are more such kind of input, there are more such kind of functions to handle your different type of variables.
But these kind of functions are only for the candidate.
No, they are available also for your standard, any other things, not a problem. Okay, I just change the regressor to DNN regressor, right? So you can see that I just have to change the DNN regressor and put hidden units. I have a neural network model. Nothing changes, only these two changes, I get a new regressor. It's very easy. People who are starting in machine learning, people who do not know much about it, want to use it as a black box, this is a great way of doing it. So I talked about embedding columns, so you can also use embeddings, right? Embeddings are done through neural networks, right? A single layer neural network. And then let's look at TensorBoard. Now you are doing training, right? So what are you generally interested in training? You are interested in how the convergence is happening, right? Correct? Whether model is learning or not. So bear with me, there are few of our friends who do not, probably they have not done gradient descent. So I'll try to explain what is gradient descent, right? So we have, can everybody see this? So we have what is called as, so this is our parameter, right? I'll keep it simple with one parameter, and this is loss. So there is a graph between what is the value of parameter and what is loss, right? And let's say I have a convex loss. I'll take a simple example, but gradient descent you can also use for non-convex functions, right? Although convergence to global minima is not guaranteed, okay? And okay, so the way gradient descent algorithm works, it's very intuitive and very interesting idea. So do you do trekking? Right, you go to the hilltop, right? And now you want to come down, right? What do you do? So now, right, I look around and I figure out the direction of the steepest descent and follow that direction, right? So exactly the same idea is applied in gradient descent, right? So I need to find out optimal, I want to find out optimal value of theta that minimizes my loss, right? Obviously we can see that this is the point, right? So we have an iterative algorithm, right? We start here somewhere, anywhere, let's say I start here, right? And at this point, I will find out gradient of the loss function, right? And let's say this is the gradient of the loss function, right? And then I take steps in the direction of gradient, correct? Now, learning rate defines how far I want to move in the direction of loss function, in the direction of gradient, right? Even though this is a very steep slope, I don't want to jump and reach at the end of the slope, something like that. Right? So I want to decide how much I want to move in that direction. Right? So typical update in gradient descent is you set your theta to theta minus alpha times del theta of j theta. Right? So this is a partial derivative, right? So the gradient that I find, and I multiply that gradient with a learning rate, right? Now, is gradient descent even for convex function, is it guaranteed to converge all the time? It depends on the learning rate, right? So if you take small steps, you will probably reach here. But what if you decide to take big steps? Yeah, you will oscillate, right? You might go like this, come back like this. Correct? So choosing the right learning rate is very important, both from efficiency perspective and from getting a convergence perspective, right? So you have this tool, right? So you want to probably look at, so this is my epoch, right? And this is my loss, right? So for every epoch, there is some loss, right? As I start training, this should ideally decrease. If you are getting something like this, you are good, right? Then you have right learning rate. But if you get something like this, it's a red sign for you, right? This is a signature of oscillation, right? Loss is coming down, going up, very bad. So if you find this, reduce your learning rate, right? If you find this curve too flat, that means it's learning very slowly, right? Then you have scope of improving the learning rate. Put slightly higher learning rate, and then you will get faster to the optima. Why learning is possible? Why is learning possible? Huh? What are the assumptions that we make? We say that training data and test data comes from the same distribution, IID, independent and identically distributed, right? So there is one source which is giving you training examples. If that assumption is true, why do I really need to go through all the data again and again, right? I can, instead of going through the entire data, I batch the examples into smaller batch size, let's say of 1000, right? And I process batch of 1000, get one update, right? That's stochastic gradient descent. And when I'm doing stochastic, no, that's a mini batch gradient descent. When I'm doing mini batch gradient descent, there is a possibility that you might see some such kind of temporary thing. And the other extreme is I take one example at a time and make update. That's stochastic gradient descent, right? And one example, it's not so stable. That's why we always use mini batch gradient descent for practical purposes. And if you know gradient descent, you can optimize any learning objective of any machine learning algorithm, okay? That may not be the most optimal thing to do, but then you have one tool that is applicable for all the cost functions. Have you at least trained one machine learning algorithm? Each one of you? Right? And, did you look at the loss? If you are training, let's say, linear regression, did you look at what is the squared error after every iteration? Right? So you want to look at that, right? So TensorBoard is a place to look at, right? TensorBoard is a tool that comes with TensorFlow, where all these statistics are gathered and showed them to you, right? So you can see, let's say some of the summaries or some of the objects, right? You can also see how different variables are changing across epochs. So this shows how bias is changing, right? It also has graphs for accuracy and other matrices, like precision, recall, F measure, right? So you have all those graphs in TensorBoard. So this is a very powerful tool. You don't have to, let's say, write another visualization routines in Python to visualize your learning statistics. Okay, so now it's your time. So go to, have you cloned this repository on the GitHub? Each one of you have cloned the GitHub repository? Okay, so go to the workshops notebook that is for canned estimator. I will first walk you through this canned estimator notebook, right? And then you can try it on your own, right? Feel free to make changes, explore, print various things and experience TensorFlow yourself, right? So in this particular exercise, what we are going to do is, we are going to write a classifier to detect handwritten digits, to recognize handwritten digits, right? So there are 10 classes, 0 to 9, right? So there is a standard MNIST data set for handwritten digit recognition. We'll be using that. So we'll be using a Keras function, Keras dataset function to load the data, right? It will return you training and test set, right? And then we'll be using NumPy input function to input my training data and test data. And finally, I'm going to have a feature specification. Each of my feature column is a numeric. So I have a numerical column. So essentially, each image in this data set is a 28 by 28 pixel, right? So I'll linearize it and I'll make it into 784 dimensional vector, right? And then I specify linear classifier. So this linear classifier is nothing but a logistic regression classifier, okay? So which takes the feature specification and number of classes, which is 10, right? And then I train using 1000 steps, and then I will look at what is the accuracy of that. Yeah, let's start, okay? And then we'll also train, we'll also build a deep neural network classifier and check the accuracy with deep neural network classifier. And you will compare accuracies of two classifiers on the MNIST digit dataset. Okay, right? If you have any questions, you can feel free to ask us. Okay, let's take about 15 minutes or take 20 minutes to finish this lab. Let's look at standard process of machine learning. So now the first exercise we did was with images, right? Now let's look at structured data. Structured data you will encounter at different places. Let's say data that is stored in database or in some files, and we are often required to build machine learning models on it. So we will take one such data set. This is a housing data set. Okay. I will show you a couple of tools. One is this Facets. At least talk about it. So Facet is a tool that you can use to visualize and explore your data. Okay. And so the data set that we are going to look at is adult data set, where we will try to predict what is the individual's income. And this will be solved as a classification problem, where we will say that we want to predict whether income is more than $50,000 or not. Okay. Okay. So this requires us to download data from the internet, right? And again, we'll use Keras utils package to get training data and test data. And the data set is there in UCI repository, right? And it has got multiple columns like age, work class, education, occupation, and so on, right? We'll load data using pandas, right? And then we'll apply the first pre-processing. So any missing values, if they are there, we will drop NAs, right? And then we will separate the labels from the feature in this, right? So we will get the income out of the vector, and we do one sanity check. We find out what are the shapes of training data and label data, right? So you can see that we have same number of examples and labels, same with test and test examples and labels. And the head command, the pandas head command. Do you know pandas? How many of you know pandas? Okay, pandas is another package, data frame package. Do you use Python? Have you seen data frames in Python? Data frame is kind of a versatile data structure that can store data of different type. Right, so you can think of it as a collection of dictionaries or a collection of lists. So you can have float values in the first column, you can have character value in the second column and so on. So that is data frame, right? So the head command will print first 5 rows. So you can see that there is age, there is work class, education and so on, right? And we can also in the same manner look at first few entries of the label column. So you can see that there is a false and true labels here, right? And this false and true we got by applying a lambda function wherever it is greater than where the income is greater than 50K, we said that we want true or else we want false. Okay, right? And then now we have training input function and test input function using pandas input function, right? Because our data is now in pandas, we'll use input.pandas input function from estimator to get the input. One of the very important thing in machine learning is feature engineering, right? So you have raw features. Sometimes those raw features are not sufficient. You want to, let's say, do one-hot encoding, right? Or you want to combine 2 features. These are examples of feature engineering, right? So we'll do feature engineering, and feature columns is we talked about feature column. Feature column is a preferred way of taking input into TensorFlow programs. Right, so we are going to define our feature columns. For every input column, we have to define a corresponding feature column. Right, so we have a numeric column for age. Right, then you can see that if you feel that now look at the age. Right, so what happens is that whenever we are kids, we are not earning anything. Right, so our income is 0. Then as we start our career, our income starts growing up. Right, and then there is a peak, and then we retire, and then there is no income there. So you can see that there is some kind of a nonlinear relationship between income and age. So we decide to bucketize, let's say, income, right? So I can take the age and define a bucketized column, right? So bucketization will happen automatically. So you have to specify what kind of buckets you want to create. So you have to specify bucket boundaries. So right, age less than 30, 31, age less than 46, 60, 75, 90. These are the ranges. Based on the age value, a particular bucketized column will be created for me, and I'm appending the bucketized column to feature column, right? Then sometimes you also have categorical data with vocabulary list. For example, degree, right? So there are a bunch of degrees like bachelor, 11 pass, HS grade, masters, right? Doctorate, all these degrees, right? So there is a fixed dictionary of vocabulary. Based on the vocabulary, you want to assign values to the categorical data. So categorical column with vocabulary list is the function you should be using, where you can specify your vocabulary list and get a value for your education. Okay. Then you can also do in the same manner, you can hash your categorical data into finite buckets, right? And cross column is very interesting, right? In linear regression, we fit a line, right? We fit a line as a function. Let's say if I want to fit the second order polynomial, how do you do it with linear regression? Yes, I do feature crosses, right? Let's say I have x is my feature, I'll square that particular feature, x square, x1 square. If I have two feature x1, x2, I'll do x1 square, x2 square and x1, x2, right? So essentially taking the cross product of the feature, right? So if you say crossed column between age bucket and education bucket, I will create automatic cross between age bucket and education, right? And then I can append that, right? And then you can create a canned linear estimator, use linear classifier, and then you know what to do, right? We train the classifier, right? And then we evaluate the estimator on the training data and on the test data, and we look at various statistics. And once we have the model ready, you can use it to predict for the test data. Right? So go through this Colab, right? And in the same manner, I can define a deep neural network model where I can do feature embeddings. So that is the second part of this lab. So I would request you to go through the Colab, read the documentation, do the experimentation, right? And we are around to help you out anyways. Okay. So after this, this concludes the basic part of the workshop, where what we learned is we learned about the basics of TensorFlow, and we also talked about how to use TensorFlow like scikit-learn APIs. Right? So people who want to learn basic, I mean, I would ideally like everyone to stay till the end of the workshop. But people who just want to learn basics, I mean, we are done with basics. In the second half of the workshop, we will try to write our own machine learning models using Layers API. That might be interesting for many of you who are doing research and who aspire to build new machine learning algorithms and models. So second part will be extremely relevant for those people.